Right now, sitting in that chair, you are on fire. Not the kind of fire you're thinking of, not flames, not smoke, but the same process and the same essential chemistry is happening inside you at this very moment. You are burning, slowly, quietly, impossibly elegantly. You are combusting. Glucose meeting oxygen, bonds breaking, energy released, carbon dioxide exhaled. And you don't even notice. You sit there thinking about what you're going to have for lunch while inside your cells, trillions of tiny explosions are keeping you warm, keeping you conscious, keeping you you. Now, here's what I want to ask you today. When that fire goes out, what happens? Not to you, not to your soul, not to whatever metaphysical entity you believe or don't believe in. I'm not qualified to speak on that. But what happens to the machinery? What happens to those atoms, the specific, particular atoms that right now are arranged in the improbable configuration we call a human being? Where do they go? What becomes of them? And is there something in the answer to that question, something in the cold, hard, beautiful physics of it, that might be worth calling, in some very careful sense, immortality? I want to take you on a journey today. We're going to start with something you can see with your naked eye, and by the time we're done, we will have traveled to the interior of a dead star. We will have talked to Lavoisier, the man who understood fire and lost his head for it. We will have sat with the strange fact that the iron in your blood was forged in a supernova explosion. And somewhere in all of that, I think we will find something genuinely astonishing, something that doesn't require you to believe anything, something that is simply, demonstrably, heartbreakingly true. Let's start with a candle. I love candles, not for romantic reasons, though they're fine for that too, but because a candle is one of the most philosophically interesting objects in the world. In 1848, Michael Faraday gave a series of lectures at the Royal Institution in London called The Chemical History of a Candle. He was talking to children, actually, and he spent 6 full lectures, 6, unpacking everything that happens when a candle burns. 6 lectures on a candle, because the universe is not shallow. Nothing in the universe is shallow if you look at it honestly. Now watch what happens. You light a candle, the flame appears, something is clearly happening. You can see energy being released, you can feel the heat. But here's the question. Faraday kept asking, where does the candle go? You've probably noticed that a candle gets shorter as it burns. The wax disappears. But where? It doesn't fall on the table. It doesn't pool on the floor. It seems to simply vanish into thin air. And this is exactly right. It does vanish into thin air. The wax, which is a long chain of carbon and hydrogen atoms, reacts with oxygen from the atmosphere. And the products are carbon dioxide and water vapor, both of which are invisible gases, both of which float away. The solid candle becomes invisible gas and drifts off into the room and then out the window and then into the broader atmosphere. The candle isn't gone, it's just dispersed. Now keep this idea, dispersion, in your mind, because it is the key to everything I want to tell you today. Antoine Laurent de Lavoisier understood this better than anyone who had ever lived. He was a French nobleman, a tax collector by trade, and the greatest chemist of the 18th century, a combination of vocations that would eventually get him killed, but we'll come to that. Lavoisier is the person who understood, really understood, what burning is. Before him, scientists believed in something called phlogiston, a hypothetical substance they thought existed inside flammable materials and was released during burning. When wood burned, phlogiston was escaping. When metal rusted, phlogiston was leaving. It seemed reasonable. It explained the observations, more or less. Lavoisier did something that sounds obvious now, but was revolutionary then. He weighed things. Before the reaction, after the reaction, he kept careful track, and he found something that shattered phlogiston forever. When substances burn or combine or decompose, the total mass, the total weight of everything involved doesn't change. The candle loses mass, but the gases it produces gain the exact same mass. Nothing is created, nothing is destroyed, just rearranged. He called this the law of conservation of mass. We now know it's one piece of a deeper truth of the conservation of mass energy, but the basic insight was his, and it was one of the most important intellectual achievements in human history. Matter doesn't disappear. It can't. It transforms. It moves around. It changes form, but it is never, not once, annihilated. Lavoisier was guillotined in 1794 during the French Revolution. His former career as a tax collector made him unpopular with the new regime. The mathematician Lagrange said afterward, "It took them only an instant to cut off that head, and 100 years may not give us another like it." The judge, at his trial, was famously quoted as saying that the revolution had no need of scientists. There is a kind of terrible irony there that I find instructive. The man who proved that matter is conserved had his own matter, the specific arrangement of atoms that was Lavoisier, permanently dispersed by a blade, and yet his ideas survived. His insight survived. In some real and important sense, his work is still present, still doing things in the world, but I'm getting ahead of myself. Let's come back to the question, what are you physically? What is the material you? At the most basic level, and I mean truly basic, no metaphors yet, you are approximately 7 billion atoms. That's a 7 followed by 27 zeros, an incomprehensible number. You are mostly hydrogen. Something like 60% of your atoms, by count, are hydrogen. The lightest and most abundant element in the universe. You have a lot of oxygen, a lot of carbon, some nitrogen, smaller amounts of calcium, phosphorus, potassium, sodium, chlorine, and a handful of others in trace amounts, iron, zinc, iodine, and so on. These atoms are arranged into molecules, the molecules into cells, the cells into organs, the organs into you. Right now, reading this, sitting in this room, you are a specific arrangement of those atoms that has persisted more or less continuously for however many years you've been alive. But here's something that might surprise you. You are not the same atoms you were 10 years ago. I don't mean this metaphorically, I mean it literally. The specific atoms currently in your liver are not the atoms that were in your liver in 2015. Your body is constantly breaking itself down and rebuilding. Red blood cells live about 120 days. The cells lining your gut are replaced every few days. The atoms in your bones are exchanged over years. Even most of your neurons, which persist as cells much longer, are constantly replacing the molecules within them. Your body is less like a sculpture and more like a flame. The form persists, the matter flows through. There's a beautiful thought experiment I want you to sit with for a moment. Suppose you could tag one oxygen atom, just one, in your body right now. Put a little flag on it, metaphorically. Follow it over the next decade. That atom will cycle through your bloodstream. It'll be incorporated into a water molecule, be used in a chemical reaction, be exhaled as carbon dioxide through your lungs, float out into the atmosphere, be absorbed by a tree, become part of a leaf, fall to the ground in autumn, be consumed by bacteria in the soil, leach into a river, be drunk by a deer somewhere in Pennsylvania, incorporated into that deer's muscle tissue, and so on, essentially forever. The atom doesn't know it's doing any of this. It doesn't have a preference. It just follows the rules of chemistry and physics, bouncing around the world with absolute impartiality. And the same is true when you die for all your atoms. When a body decomposes, and I want you to stay with me here because this is not morbid, this is actually beautiful, it is being slowly disassembled. Bacteria and enzymes break the long, complex molecules into simpler ones. The carbon in your cells combines with oxygen and becomes carbon dioxide, which enters the atmosphere. The nitrogen becomes part of the soil. The calcium in your bones persists longer. Bones can last thousands of years under the right conditions, but eventually even those are absorbed, dissolved, dispersed. The process is essentially the candle in reverse. Instead of organized energy releasing heat and light and becoming gas, organized matter is becoming disorganized again, returning to a simpler state, releasing the chemical energy stored in all those complex molecules, feeding other organisms, entering cycles that have been running for billions of years. Now here's where I want to pause and point out something you might have missed. We just said that the process of decomposition feeds other organisms. Think about what that means. The carbon that is released when you decompose will be taken up by plants through photosynthesis, which is itself one of the most remarkable processes in nature, pulling carbon dioxide out of the air and using sunlight to build it into sugars. Those sugars will be eaten by animals. Those animals will be eaten by other animals. Your specific atoms will become part of other living things. This is not poetry. This is not a comforting story someone made up. This is the actual, documented, biochemically verified pathway of atoms through ecosystems. Ecologists have traced isotopes, special versions of atoms that you can track because they're slightly heavier, food webs. They've watched nitrogen from decomposed animals show up in the needles of trees miles away. They followed carbon through multiple generations of organisms. The atoms move, they cycle, they return again and again to the living world. Every atom in your body has been part of something else before it was part of you. The carbon in your DNA was once CO2 in the atmosphere before a plant grabbed it and turned it into a sugar molecule. Before you ate that plant, or ate something that ate that plant. The iron in your hemoglobin, and here is where we arrive at the truly staggering fact I promised you earlier, was forged in a star. I need to stop and say this more clearly because it is too important to rush past. The iron in your blood was not present at the beginning of the universe. When the universe began approximately 14 billion years ago, the only elements that existed were hydrogen, helium, and tiny amounts of lithium. The periodic table was almost empty. All the heavier elements, carbon, oxygen, nitrogen, iron, calcium, did not exist yet. They had to be made. They were made inside stars. A star is, at its heart, a nuclear furnace. Hydrogen is fused into helium. Helium is fused into beryllium and carbon. Carbon is fused into oxygen and neon. Heavier and heavier elements are built up step by step through this process of nuclear fusion. The star is essentially manufacturing the periodic table. Our own sun can only get so far. It will eventually produce carbon and oxygen and some heavier elements, but it will never reach iron. Iron is special. Iron is where stellar fusion stops. Iron is the most stable atomic nucleus. It sits at the bottom of the nuclear energy landscape. To fuse iron into heavier elements requires energy rather than releasing it. So when a massive star builds an iron core, it has reached a dead end. It can no longer generate energy from fusion. And what happens then is cataclysmic. The core collapses. In about a quarter of a second, think about that, a stellar core the size of Earth collapses down to something the size of a city. The density becomes incomprehensible. Protons and electrons are crushed together into neutrons. The infalling matter bounces off this newly formed neutron star, and the rebound tears the outer layers of the star apart in an explosion so powerful it briefly outshines the entire galaxy. This is a supernova. In the moments of a supernova explosion and in the exotic conditions in neutron star mergers, which we now know also produce heavy elements, the nuclear reactions can synthesize every element heavier than iron. Gold, silver, lead, uranium, all of it cooked up in the extreme conditions of dying stars and then blasted out into space in the explosion. This material drifts through the galaxy as a gas cloud. Eventually, gravity pulls some of that cloud together. It collapses under its own weight, heats up, ignites. A new star forms. If the cloud is large enough and has enough angular momentum, a disk of leftover material forms around the new star. Dust grains in that disk collide and stick. Small rocks form. Small rocks become large rocks. Large rocks become planetesimals. Planetesimals collide and merge. Planets form. One of those planets, a small rocky one, third from a modest yellow star in a spiral arm of the Milky Way, turned out to have liquid water and a nice temperature range and a protective magnetic field, and after about 4 billion years of biological evolution, people. You are the universe looking at itself. Your iron. The iron that carries oxygen through your blood, the iron that makes your hemoglobin red, was made in a star that exploded before our solar system existed. You are literally made of stardust. And I know that phrase has become a kind of cliche, a thing people put on motivational posters. And I want you to understand that I am not saying it as a metaphor. I am saying it as a statement of nuclear astrophysics. Your atoms were in stars. Some of your atoms have been in multiple stars. You are the current address of matter that has been traveling through the universe for billions of years. Now, back to the question of what happens when you die. Your atoms, these ancient, well-traveled atoms, disperse. They enter cycles. They become parts of other things. They cycle through the atmosphere, through the ocean, through the biosphere. Some of them will be incorporated into other living organisms within years. Some of the heavier elements in your bones might persist in one form or another for geological timescales and millions of years. Eventually, in the very long run, they'll be in the ocean, in the Earth's mantle, cycling through geological processes we can barely imagine. And in the truly long run, 5 billion years from now, when our sun becomes a red giant and its outer envelope expands to engulf the inner planets, those atoms will be dispersed back into space. The universe is patient. The universe keeps its books. And here I want to tell you about something that I find personally very moving, which is the concept of the carbon cycle and what it means for the question of identity. Right now, as I'm speaking to you, every breath you exhale contains carbon dioxide, carbon that was recently part of you. That carbon is now in this room. Some of it will be absorbed by plants outside. Some of it will dissolve in water and eventually reach the ocean. Some of it will be breathed in by other people, perhaps in this room right now, perhaps years from now. Every person in this room has breathed in atoms that were once exhaled by, let's see, Julius Caesar, or Marie Curie, or Shakespeare, or the first human being who ever looked up at the night sky and wondered what the stars were. I don't know exactly where those specific atoms are right now. I'd have to do a lot of very careful tracking. But the math is clear. There are so many atoms in a breath, and those atoms have been cycling through the atmosphere for so long that it is statistically near certain that every breath you take contains atoms that were once in other human beings, in all kinds of human beings, in all the great and terrible people who have ever lived. This is not comfortable necessarily. It means you're sharing your material with everyone, with people you'd prefer not to share with. But the universe doesn't care about your preferences. The universe is magnificently indifferent to our social distinctions. Now, there's a question I've been dancing around, and I want to approach it directly. When we talk about immortality, when people use that word in the context of death and what persists, what do they usually mean? They mean continuity of self, the persistence of the particular configuration, the particular memories, the particular consciousness that makes you you. And I am not going to stand here and tell you that your atoms being dispersed into the biosphere is the same thing. It isn't. The specific pattern breaks down. The memories don't persist in the atoms. The personality isn't stored in the carbon. I think it's important to be honest about this. The kind of immortality the atoms give you is not the kind most people are hoping for when they ask the question. But here is what I want to offer instead. Here is what I think is actually more interesting. There are, as far as we know, a finite number of atoms in the observable universe. A very large finite number, something like 10 to the 80, but finite. Those atoms have been here since shortly after the Big Bang. They've been rearranged over and over for 14 billion years. They've been hydrogen gas in nebulae. They've been the cores of stars. They've been supernovae. They've been interstellar dust. They've been part of primitive chemistry in the early solar system. They've been part of the first self-replicating molecules, the ancestors of DNA. They've been bacteria. They've been algae. They've been ferns. They've been dinosaurs. They've been mammals. They've been somewhere in that chain, the ancestors of every human being who has ever lived. And right now, in this particular moment in the history of the universe, some of those atoms are arranged into you. A specific configuration of atoms that can ask this question, that can sit in a room and wonder about its own mortality, that can feel the weight of the question, that can find the answer beautiful or terrible or both. The universe has been rearranging these atoms for 14 billion years. And in all that rearranging, it has in some places produced things that can wonder about themselves. That seems important to me. I don't know exactly what to do with it, but it seems important. Now, I want to talk about energy because we've been talking about matter and I've been leaving out the other half of the story. When you eat, when you consume food, you are taking in chemical energy. The energy stored in the molecular bonds of carbohydrates, fats, proteins. That energy was originally solar energy captured by plants through photosynthesis. The sun radiates energy, electromagnetic radiation, photons, and some of that radiation hits a leaf and drives a chemical reaction that stores the energy in the chemical bonds of sugar. You eat the sugar. Your cells break those bonds in cellular respiration and capture the released energy in a molecule called ATP, which is the universal energy currency of life. Your muscles use ATP to contract. Your neurons use it to fire. Your heart uses it to pump. All of this energy is ultimately solar energy. You are, in some technical sense, a machine that runs on sunlight. Now, here's something interesting about energy, and this is where Lavoisier's insight gets extended by another century of physics. Energy, like matter, is conserved. The total energy in a closed system doesn't change. It can be transformed, kinetic to potential, chemical to thermal, electrical to mechanical, but it doesn't disappear. When you die and your body cools and the metabolic reactions stop, what happens to the energy? It dissipates. It becomes heat, heat that radiates out into the environment, that warms the air slightly, that eventually radiates out into space. The specific organization, the intricate network of chemical reactions that is a living body comes apart. The energy that was driving those reactions spreads out into the environment in a much less organized form. This is entropy. And entropy is, I think, the most profound concept in physics, more fundamental than gravity in some ways, more universal. The second law of thermodynamics tells us that in any closed system, the disorder tends to increase. Things naturally go from organized to disorganized, from hot to cold, from useful energy to waste heat. A living body is a pocket of extraordinary order, maintained against this relentless tendency toward disorder by constantly taking in organized energy. Huts. Food. Expelling disordered energy. Boom. Heat and waste products. When the organism dies, it stops fighting entropy, and entropy wins. But here's what entropy doesn't tell you. It doesn't tell you that the disorganization is permanent, because the universe is not a closed system, or rather, our corner of it isn't. The sun is pouring energy into the earth every second. Plants capture some of that energy and use it to build organized structures themselves. And some of those structures get eaten, and some of what gets eaten becomes more organized structures. The arrow of entropy points one way for the system as a whole. But locally, temporarily, magnificently, life swims upstream. Life creates order. Life takes dispersed atoms and pulls them together into patterns of breathtaking complexity. It has been doing this for 4 billion years, and somewhere in that 4 billion year history of life on Earth, the process has produced organisms, first very simple ones, then increasingly complex ones, that store information about the environment they're in, that modify their behavior based on that information, and eventually, in the case of creatures like us, that develop internal models of themselves and of the world, that develop language, that can transmit those internal models to other organisms, not just through DNA, but through words, through symbols, through art, through science. The atoms die, but the patterns, the information, the ideas, that's where it gets philosophically interesting. That's where it gets genuinely complicated, because a pattern, unlike an atom, can be copied. The specific arrangement of atoms in your brain is not copyable, not transferable. But the information those atoms encode, your thoughts, your insights, your discoveries, whatever understanding of the world you manage to wrest from it in your years of being alive, that information doesn't have to die with you. Lavoisier is dead, his atoms are dispersed, but his insight, the law of conservation of mass, is still doing work in the world, still informing every chemistry student who learns it for the first time and feels the satisfying click of an important thing becoming clear. Is that immortality? I honestly don't know what to call it, but it's real, it's something. There's a moment in physics, and this is one of my favorite stories, when Erwin Schrödinger, who gave us quantum mechanics and a very famous cat, sat down in the 1940s and wrote a small book called What is Life? He was asking the question from a physics perspective. What is it physically that distinguishes living matter from dead matter? What does a living organism do that a rock doesn't? His answer, which was remarkably prescient given that he wrote it before the structure of DNA was known, was that living organisms feed on negative entropy. They take in order from the environment and use it to maintain their own internal order. He predicted essentially that there must be a molecule that stores information in a stable form that can be copied reliably, that can encode the instructions for building an organism. He didn't know what it would look like. He called it an aperiodic crystal. 9 years later, Watson and Crick found it. It was the double helix. DNA is the universe's way of storing the pattern even as the atoms cycle through. The specific atoms in your DNA today are not the same atoms that were there when you were born. They've been replaced over and over, but the pattern, the sequence, the code, is faithfully copied every time a cell divides. The information persists even as the matter flows. This is remarkable enough that I want to sit with it for a moment. The information is more stable than the material that encodes it. The pattern outlasts the particular atoms. Your body is, in this sense, a pattern that has been perpetuating itself through continuously flowing matter for your entire life. And some of that information, and not the DNA sequence, but the higher level information about your experience of being you, gets encoded in the pattern of connections in your brain, the specific way certain neurons connect to others, the weights of certain synaptic connections. This is what we mean physically by memory and personality and identity. Not specific atoms, patterns, but these patterns, unlike DNA, are not currently copyable. We don't know how to read them out and transfer them elsewhere. And when the matter that encodes them disperses, they go with it. The specific network of memories that makes you dissolves when the neurons that encode it dissolve. This is the loss. This is what death actually is from a physical standpoint. Not the loss of atoms, those are indestructible, they go on, but the loss of a particular arrangement, the dissolution of a pattern that took decades to develop. That is absolutely unique. That contains information about a specific life that no other collection of matter has ever contained and will never contain again. That is worth grieving. That is a real loss. And I don't want to minimize it by rushing to the compensatory points. But since we're being honest about the whole picture, let me offer the compensatory points. The atoms go on. They go on into the world and they become parts of other things. Some of those things will be living. Some of those living things will be conscious. Some of those conscious things will ask the same questions we're asking here. There is a sense, genuine, physical, verifiable, in which the matter that is you will be part of the living world for as long as the living world persists. This is not metaphor. This is biogeochemistry. The energy goes on too, not in a usable form, dissipates into heat, into the thermodynamic background, but it's still there in a sense because the total energy of the universe is conserved. Every joule of energy you've ever used is still somewhere in the universe, still contributing to the great accounting. And the information, the ideas, the understanding, the ways of seeing the world that you develop in your life, this is the most interesting case because information, unlike atoms, can be genuinely copied, genuinely transmitted. Every teacher who ever changed a student's way of seeing the world achieved a kind of persistence through that transmission. The student carries something of the teacher's way of seeing and may transmit it to others and so on, propagating not atoms but patterns through time. This is what science is in some ways. Science is humanity's most systematic attempt to extract patterns from nature and encode them in a form that persists in language, in mathematics, in books, in institutions, so that each generation doesn't have to discover everything from scratch. The specific neurons that fired in Newton's brain when he understood gravitation are long gone. But the understanding persists. It has been transmitted to hundreds of millions of people. It is encoded in the mathematics that guides spacecraft to other planets, the pattern propagated. There is something in this that I find genuinely moving, and I'm not sure I can fully articulate why. Maybe it's this. We live in a universe that appears to have no inherent obligation to be comprehensible. There's no obvious reason why the laws of physics should be describable in mathematical equations that human brains can understand. There's no obvious reason why the universe should have produced creatures capable of asking these questions at all, and yet here we are. These atoms bouncing around, according to the laws of physics, have somehow arranged themselves into beings who can ask why they're here, who can understand, at least in part, the processes that produce them, who can look at a candle and spend 6 lectures wondering where it goes. I don't know what to make of that, honestly. It seems too remarkable to be an accident, and yet I know from the physics that it is in some sense an accident, a contingent outcome of a very long chain of physical events, and I hold those two things in my head at the same time, and I can't resolve them, and I've decided I don't need to. The wonder is enough. The strangeness is enough. Let me come back to something I said at the beginning. Your atoms have been in stars. They've been in the ocean, in the atmosphere, in other living things. They've been part of the long, improbable story of matter arranging itself into more and more complex configurations. They are on loan to you, to the particular configuration that is you, for the duration of your life. And then they will be dispersed, and they will go on to be parts of other things. But this is the thing I want to leave you with. This is what I've been building toward. In roughly 100 billion years, give or take, the last stars will burn out. The universe will have expanded and cooled to the point where new stars can no longer form. All the remaining matter will slowly decay into its most stable forms, iron and nickel, mostly, those elements at the bottom of the nuclear energy landscape. Protons themselves may decay over timescales almost beyond imagination. Eventually, in the truly far future, the universe may reach a state of maximum entropy, cold and dark and almost uniform, with nothing left to do any work, nothing left to sustain any complexity. Your atoms will be part of that story. In the very long run, they will be iron. They will be part of the uniform, cold substrate of a used-up universe. This is sometimes called the heat death of the universe, and it sounds bleak, and in some ways, it is. But we are not living in the far future. We are living 14 billion years into the history of a universe that is still wildly, extravagantly productive. There is still an enormous amount of order being created locally in the light of 100 billion galaxies. There is still, on this small planet, a biosphere of tremendous complexity and diversity, continuously creating organized structures out of flowing matter and solar energy. There are still beings, these bizarre and precious configurations of atoms, capable of feeling and wondering and understanding. You are one of those configurations right now. Today, the atoms that are you will be rearranged. The pattern that is you will dissolve, but the matter will persist. And the universe that produced you will keep producing remarkable things for billions of years. You are made of ancient star stuff, briefly organized into something that can know this about itself. And then, after a while, the star stuff goes back. I find that not comforting exactly, but true. And the truth of it is something. It's a kind of membership. You are not separate from the universe, looking at it from outside. You are the universe. You are a local, temporary whirl of matter and energy that has somehow achieved the improbable trick of comprehending itself. And if you ask me whether that is enough, whether that is sufficient as a story, as a framework for living, I can't answer that for you. You have to decide that yourself. The physics doesn't tell you how to feel. The physics just tells you what's true. What's true is that you are made of atoms that have been everywhere and will go everywhere. What's true is that those atoms are conserved. Lavoisier was right. They are not destroyed. They persist. They cycle. What's true is that the energy that animates you came from a star and will return to the general thermal background of the universe. What's true is that in all the 14 billion years of this universe's history, there has never been another configuration of atoms exactly like you, and there will never be again. The question I want to leave you with is not one I can answer. It's one I've been carrying for decades, and I'm no closer to an answer, and I've come to think the carrying is the point. The question is this: we have established that matter is conserved, that atoms cycle, that patterns persist in DNA and in transmitted knowledge. But we have also established that the specific pattern, the one that contains your memories, your consciousness, your particular way of experiencing being alive, that pattern dissolves when you die. And so the question is, what is that pattern? What is it that has it? Does the universe contain only the atoms, or does it also contain, in some sense we don't yet understand, the fact that some of those atoms are currently arranged so as to experience something? That's the hard problem of consciousness. And I don't have an answer. Nobody does. Not yet. And I find the not knowing, the siktokos to and the staring into that particular abyss and admitting I can't see the bottom more honest and more exciting than any of the premature answers people have offered. The universe is not obligated to be fully comprehensible, but it has given us enough to see its outlines, enough to understand that we are temporary and ancient and continuous and unique all at once. Go home tonight and look at your hand. Those atoms, those specific atoms, were in stars. They were in the ocean. They were in other creatures, ones that couldn't ask these questions. And now they're arranged into something that can. That doesn't last forever. Nothing does. But right now, at this particular moment in the history of the universe, that arrangement is here. That arrangement is you. Isn't that something? There's one more thing I want to tell you because I think it changes the texture of everything else I've said. Physicists have recently gotten very good at detecting something called gravitational waves. These are ripples in the fabric of space-time itself, produced by massive events, colliding black holes, colliding neutron stars. In 2017, we detected gravitational waves from two neutron stars spiraling into each other and merging. And at the same time, we saw a burst of light from the same event. And when we analyzed that light, when we looked at the spectrum, at what wavelengths were being emitted, we found gold. We found platinum. We found strontium. We watched heavy elements being created in real time in an event 130 million light years away. We didn't just have a theory that your gold ring came from a neutron star merger. We watched it happen. I find that almost unbearably wonderful. We detected the birth of the atoms. We caught the universe in the act of manufacturing the periodic table, and the same process and the same kind of cataclysmic collision produced the gold and the platinum and the heavier elements in your body before our solar system was born. You didn't just come from stars, you came from the most violent events in the known universe. Your atoms were cooked in stellar cores and blasted out in supernova explosions and forged in the collision of neutron stars. If you wanted to make a human being from scratch, you would first have to make several generations of stars, let them live and die, scatter their contents across the galaxy, wait for gravity to gather that enriched material into a new solar system, wait for a planet to cool and for chemistry to get complicated, and then wait 4 billion years for biology to work its way up to something that could ask the question we started with. You are the punchline of a 14 billion year joke, and the joke is beautiful. Now, here's the very last thing. I want to say it simply, without qualification or apology. We don't know what consciousness is. We don't know how it arises from the physical arrangement of neurons. We don't know whether it's something in addition to the physical pattern, or whether the pattern is all there is. We don't know whether the universe is just matter and energy, or whether there is something it is like to be a certain arrangement of matter and energy, something extra, something irreducible. This is not a deficiency in science. This is an active and honest acknowledgement of a genuine mystery. The hard problem of consciousness is hard precisely because our current tools, the tools of physics and chemistry and neuroscience, seem to illuminate everything around the experience of being conscious without quite touching the experience itself. We can explain what the brain does without, so far, fully explaining what it is to have a brain, to be the thing that looks out through those eyes. And this matters for the question of death because it means we genuinely don't know what is lost when a mind stops. We know the atoms disperse. We know the neural patterns dissolve. But whether something additional, the experience of being that person was present and is now absent, or whether that something additional was just another name for the neural patterns, we don't know. I'm comfortable not knowing. I've been comfortable with uncertainty my whole life. I think the willingness to say, I don't know, genuinely without flinching, is one of the most important scientific virtues there is. It keeps you honest. It keeps you looking. The atoms don't hold the answer. The energy doesn't hold the answer. The patterns we can currently describe don't hold the answer. The answer, if there is one, is somewhere in the territory we haven't mapped yet. And that means the investigation isn't over. The most interesting question is still open. And I can't think of a better way to leave things than that. Open, uncertain, full of the possibility that the next piece of the puzzle is somewhere just ahead if we're honest enough and curious enough and brave enough to keep looking. Your atoms were in stars. They're on loan to you for a little while. And the universe, this magnificent, impersonal, beautiful universe, will find something else to do with them when you're done. It always does.